Being able to successfully freehand sketch a polynomial is just a matter of putting together the steps that will allow us to identify all of the key locations and patterns in a polynomial's graph. So beginning our examples, let's take a look at the function f of x equals negative 2x cubed plus 10x squared plus 8x minus 40. There are three major parts to this polynomial that we want to identify in order to graph it and give a quick sketch of what it might look like. The first thing that we're going to look for is the end behavior of the polynomial. Now you'll remember from previous lessons that we identify the end behavior of the polynomial by looking at the first term when the polynomial is written in standard form. This particular polynomial has an odd degree, that's the 3, and it has a negative leading coefficient, and that's the negative 2. Because it has an odd degree and a negative lead coefficient, we will expect this graph to look like this on its two ends. We expect it to be rising on the left side of the graph and falling on the right side of the graph. We expect the graph to be rising as x goes towards negative infinity, and we expect the graph to be falling as x goes towards positive infinity. So when we graph, we should anticipate seeing this kind of behavior on the ends. We're not trying to graph it perfectly. That's not what sketching is about. Sketching is not about being able to graph it perfectly. Sketching is about being able to get a rough idea of what the graph is going to look like. The second thing that we want to identify that would be pretty easy to identify is the y-intercept of the polynomial. If the polynomial is written in standard form and we're looking for the y-intercept, you might remember that the y-intercept is always going to start with x is equal to 0. If I make x equals 0 everywhere in this polynomial, I would expect those first three terms to just fall off. Everything or anything times 0 will make 0, which means that the last term, the constant term, will be identified as our y-intercept. And that should work provided that all of the other terms all have x's in them, which if it's written in standard form, they should. The last thing and the most difficult thing for us to identify is the x-intercepts of the polynomial. It is well established at this point that the x-intercepts, also known as the roots or the zeros, are those solutions that we find when we set the polynomial equal to 0. We will go back to previous lessons and look at the techniques that we use to solve polynomials. And in fact, in this one, we're just going to factor and try to solve those small equations at the end. We check first for a greatest common factor. We see that this polynomial has a greatest common factor of 2. 2 goes into each one of these individual terms. We're going to make life a little bit easier for ourselves, and we're going to notice that this negative right here, that the first term is negative. So we're going to take that negative when we take the 2. That will lead to sign changes throughout the rest of the polynomial. But fortunately for us, and you'll see why at the end, this is not going to change our solutions at all. All it will require us to do is change the signs throughout the polynomial. We still have the negative 2. We have 4 terms inside the parentheses, so this looks like a grouping situation. We'll look at the first pair. We'll see a common factor of x squared. If I want this to work, this second half is going to have to produce that common binomial of x minus 5. And that'll happen as long as I make negative 4 its common factor. Now we group. The x squared minus 4 belongs together. And then the common binomial. X squared minus 4 is a difference of squares. So we'll factor that polynomial one more time. And now we have reached the fully factored version of our original function, all the way down here. Because I'm looking for this polynomial at the bottom t equals 0, I'm going to set each one of these small binomials equal to 0. I don't have to worry about the negative 2 because there's no way for negative 2 to be 0. I factored that out. It's still there. It's still part of the polynomial. It's still mattered to the end behavior. But in terms of our factoring and solving, it is irrelevant to the solving of those smaller equations. So this first equation, when is x minus 2 equal to 0? When x is 2. When is x plus 2 equal to 0? When x is negative 2. And when is x minus 5 equal to 0? And that's when x is 5. So we have three solutions to this equation, -2, 2, and 5, and those are going to make up our x-intercepts. So at this point, we should be able to produce at least a rough sketch of the graph based off of the information that we identified here and the information that we identified here. Now, just as a warning, when we're doing polynomial sketching like this, we're not looking for perfection. So down here, I know way down here is going to have to be the point 0, -40. That was my y-intercept that I found. I know that my x-intercept is at -2. It is at 2. And it is at 5. Now, I am also well aware that the scaling on this graph is completely off. There is no consistency between the x-axis and the y-axis. I'm not worried about that. I am simply worried about getting a rough sketch of the graph. At this point, we can mix in our end behavior. This is the leftist most point of the polynomial that we know. This is the rightist most point of the polynomial that we know. End behavior analysis in the leading coefficient test tells us that coming out of this leftist most point, we would expect the polynomial to be doing something like that. And coming out of this rightist most point, we would expect the polynomial to be doing something like this. End behavior analysis guarantees that for us based on those dominant terms, dominant degree, leading coefficient. Now, the in-between space is a little bit trickier. In the in-between space, we have to be careful about how we connect. If I'm imagining this as coming down this way, then there's really only one option for me to get down to 0, -40. And that's to keep coming all the way down to 0, -40. I know that's a bottoming out point, that this graph is going to turn and come back up. I'm going to turn. I'm going to make my way back up to my intercept that's at 2. Maybe I don't know for sure that 0, -40 is the bottoming out point, but I have a pretty good idea that it's pretty close to it. So if I draw it like that, it's not necessarily the end of the world. I'm going to come back up here to try to get through this intercept. And now the obvious candidate, as I cross through that intercept, to be able to match this end behavior over here, is to give myself some kind of little maximum on this side. So you know that there's some kind of minimum in this space. You know that there's some kind of relative maximum in that space. You're guaranteed by the end behavior that the two ends of the graph are going to look like this, and then you fill in the middle space as best as you can. I did include a graph of, one more thing before we look at the actual graph. You'll notice no scaling. We're not about scaling the y-axis when we do this. We want to get a rough sketch to get a picture or an idea of what the polynomial is going to look like. Looking at the polynomial here, you'll see this is the actual graph of that function. You'll see that here's our intercept -2, here's 5, here's 2, and here's 5. Here's our y-intercept. No, it's not a maximum. So I misspoke before. That certainly is not that's not the minimum. That's certainly not the minimum. There's a minimum over here that's slightly to the left of that point. Would I know that necessarily? No. Are there techniques for finding that point? Absolutely. Some of them we will see in later lessons, and some of them you won't see until later courses. But there are strategies for finding those points exactly. There's strategies for finding any place that's a minimum or a maximum. But as long as you can identify those key intercepts, as long as you can identify the end behavior, you should be able to graph the polynomial.